Number 24. A sample of oxygen that occupies 1.00 times 6 milliliters. Oh my gosh. Milliliters. Let's just say that's volume 1. At 575 millimeters of mercury, P1, is subjected to pressure of 1.25 atmospheres, P2. What will the final volume of the sample be, solving for V2, if the temperature is held constant? Okay, there's my big red flag that I can use Boyle's law. I guess it'd be better to say that's my green flag. That allows me to go ahead and use Boyle's law. So this is almost exactly as easy as the other ones that we've done so far. Okay, we're still going to solve for V2, and so P1 V1 is equal to P2 V2. Get V2 by itself by dividing both sides of the equation by P2, and if with V2 is equal to P1 V1 over P2, that'll be easy enough. But what I'd like to point out is that the pressures have different units. Yeah, the pressures have different units. Now, I'm not going to be reporting my answer in terms of units of pressure, but I'm going to have to divide units of pressure here, and I need them to cancel out. Because if I set this up so that P1 is divided by P2, I'm going to be dividing millimeters of mercury by atmospheres eventually, and that's not going to allow any of those units to cancel out. And I'll have something pretty darn funky in my answer. The unit would be something like millimeters of mercury times milliliters divided by atmospheres, and that's simply not the unit for volume. So what we're going to have to do is we're going to have to convert one of these values for pressure into the other unit. Doesn't matter which way. Doesn't matter which one you do. If both pressure units are in millimeters of mercury, they'll successfully cancel. If both units are in atmospheres, they'll successfully cancel. So that does not matter. So let's just pick one. Let's convert 575 millimeters of mercury out of millimeters of mercury and into atmospheres. Millimeters of mercury cancel. So I'm left with that simple division. Come over here, calculator. 575 divided by 760. I want three significant figures. Let's go to that one. Let's go 0.757. Atmospheres. Okay, so I'll use this as P1 right there. All right, so I have V2 is equal to P1 V1 over P2. And again, I'm using this value over here that I just determined as P1. That way I have atmospheres all around. Atmospheres. There's my V1. Liters. There's my P2. It's already in atmospheres. Atmospheres cancel. My final answer is in liters. Right? No, it's not. It's milliliters. What am I doing? Milliliters. That's milliliters. How come no one told me? So, anywho, milliliters. All right, so I'm all good to do some division and multiplication. 757 times 1 divided by 1.25. Okay. Now, I do have this times 10 to the 6. So this bad boy is going to end up getting pretty darn big. And so I got to ask myself, do I want to move that decimal all the way to the right 6 times, excuse me, and report this in standard notation? Or move the decimal 1 time, make that 1 smaller, and leave it in scientific notation? I think I'm going to end up doing that. And so I have 3 significant figures, 3 significant figures, 3 significant figures. I'm going to keep it right there. All right, so that 6 tells me to go up by 1, so I'm going to go 6.06. move the decimal once, so this will become times 10 to the 5th. Okay, let me write that a little neater. 6.06 times 10 to the 5th milliliters.